Hello, and welcome to MidSun Statics Tutorial number 1, Forces and Moments in 2 Dimensions. My name is Leif, and in this series of tutorials, we're going to be walking you through a few of the basic concepts in statics that you'll need to know in order to tackle some of the design problems that we face on the team. So in this first tutorial, we're going to be briefly covering forces and moments, and then talking about how to solve for unknown forces and moments, and then finally we're going to finish off by talking about what we call a statically indeterminate problem. So many of you are probably familiar with the basic idea of forces and force balance, and statics is the analysis of systems at rest. So that means that all of the forces that we're imposing on these systems are going to end up being balanced. If I come over here and I have a box and it's just going to be sitting on the ground here, and then I'll draw a force coming straight down, call it F. We know that there's going to be sort of a restoring force from the ground. Let's call that F1. It's worth noting that for all these problems, we're just going to ignore gravity. So all the forces that we're putting in are arbitrary and really have nothing to do with where this thing would actually be positioned in real life. And we can figure out what F1 is quite easily just by summing the forces, right? So we have negative F. That negative is just coming from the assumed direction that we've drawn it. And then plus F1, you can see it's drawn in the positive y direction, if you will, if we have a coordinate system of y, x like that. And we want things to equal 0 because nothing here is moving. And so then we can find quite easily, obviously, that F1 equals F. So some of you are probably also familiar with the idea that forces are linear, and so they can be added up and superimposed upon one another. So if we just scroll down here, if we have a box, say, that's up against two walls, and then we have a force coming down here, and we'll say that that force is acting through the center of mass of this box. And let's just say that we have two restoring forces here. We'll call this one F1, and we'll call this one F2. So F here can actually be broken up into sort of component vectors, right? So we can say that F coming down here, and then we'll draw it in. We'll say it's at 30 degrees to the horizontal. We'll say that F can be broken up into two components, Fy and Fx, and by trigonometry, Fy is going to be equal to negative sine 30 degrees. We'll say negative F sine 30 degrees, and F of x is going to be equal to F cos 30 degrees. Again, that negative sign just because this is drawn in the negative direction here. And so now what we can do is, instead of just having, we don't just have one direction to sum, so we're going to actually have two equations. This is good because we have two unknowns. So we have the sum of forces in the y direction needs to be 0, and the sum of forces in the x direction needs to be 0. And this is going to be, in the y direction, we have F1 cosine of 30 degrees. And again, we can solve there for the magnitudes of F1 and F2. But now let's say we have, draw another box here, and this one's going to be quite long. Its center of mass is going to be here, but we have a force coming here. We'll call that F, and a force coming here. We'll call that F1. And so we can see that, to balance out in the y direction, F1 is obviously equal to F. But sort of from intuition, we can know that this object isn't going to be at rest, right? It's going to start to actually spin around the center of mass, around point C. And we call this sort of rotational force, if you will, we call this a moment. So I'll draw that in here. We're going to draw our moment like this, and we know that it's going to be spinning in the anti-clockwise direction, right? Because F is going to come here and push it that way, and F1 is going to come here and push it that way. And so this whole object is going to start to spin around its center of mass. It's not going to translate anywhere. It's not going to move because F1 and F are balanced, but it's going to start to spin. Okay, let's just take a moment to sort of properly define what a moment is. So if we have a point C here, and we have just this line bar, and then we have a force here of F, and we're going to have a distance here, which is R. We say that the moment around the point C is going to be m equal to F cross R. And the cross here we don't really need to worry about a whole lot, but what you need to keep in mind is that it's actually the normal component here of F to our line that's actually going to contribute to the moment. And so if we had a force coming in here from the side, we would need to remember to just take the normal component. And the moment here is going to give us units of Newton meters, which I've always found kind of confusing, because if you've taken some physics, you'll know that Newton meters is also the unit for energy, joules. And it kind of seems weird that we'd be talking about sort of this rotational force, but it's measured in joules. And we can get around that through an explanation that I quite like, which is that Newton meters isn't really strictly correct. It's actually the rotational force is measured in Newton meters per radian. So that means that kind of in the same way that force times distance is going to be is going to result in a certain amount of energy that it takes to push something. A moment times the amount that you rotate it, right? The rotational force times the amount that you have to rotate, that's going to give you energy once you multiply out this radian term. But because radians are technically dimensionless, that sort of doesn't make it into our actual units for the moment. It's also worth noting here that this cross product, that'll come into play in 3 dimensions, and really that has to do, you can put things into equation mathematically, the math will spit out which way this is going to rotate. You can also just kind of try to wrap your mind around it and kind of realize that this force is pushing it around this centroid a certain way, and that may not be the best way of doing things for more complicated scenarios, but just that sort of intuition will work fine for now. Okay, so let's draw a bit more of a complicated shape. We're just sort of going to have this L-shaped here, and we're going to have 2 forces acting on it. Down here, F1, and then here is going to be F2, and we want to evaluate the moment about C. Obviously, our X and Y forces aren't going to equal out, but we're not going to worry about that right now. You can see that F1 is going to have a contribution to C, to the moment about C, and we'll draw that in here. It's gonna try to turn things clockwise, and F2 is gonna try to turn things the other way, right? It's gonna try to turn things anti-clockwise. So this is really just to demonstrate that even though F1 is acting in the y direction and F2 is acting in the x direction, they can both contribute to a moment about C. And if we had another arm coming down here, and we had yet another force here, F3, you can see that that one is also contributing a clockwise motion. So F1 and F3, they're orthogonal vectors, but they can still contribute in the same direction to a moment about C. So now if we wanted to write the equation for this, and sort of convention is that counterclockwise is positive, we'd write the sum of moments about C. Let's say that this isn't spinning, so they're going to be equal to 0, and that's going to be equal to negative F1, let's call this R1, R2, and R3, negative 1, R1, plus F2, R2, and then again minus F3, R3. Okay, so now let's go back to statics, and we'll talk a bit about how we can use moments to help us to solve statics problems. So say I just have this line here, and I have we'll say that this is point A, point B, point C, and then I've got forces. I've got my main force coming down here. Let's actually give it a value. Let's say that this is 10 newtons, and then I've got F1 reacting there, and I've got F2 reacting here. So just by using our one equation of summing up the forces in y, we won't be able to solve this because we have two unknowns and we only have one equation. But we can create another equation because we know that we don't want to be rotating around A, right? We're saying this is a static problem, so nothing is moving. So what we can do is write two equations. We can write that the sum of the forces in y is going to be equal to 0, and that's going to be equal to F1 minus 10 plus F2. And we'll also give these distances. We'll say that this here is 1 meter, and we'll say that this length here is 2 meters. We can also say that the sum of the moments about point A is going to be equal to 0. And F1, because there's no moment arm, right? It's acting at A. It doesn't contribute at all to this moment. So what we have 10 newtons, and this is going to create a clockwise force. So we're going to say that this is negative again. So negative 10 times 1. And then F2 is creating a counterclockwise force, so it's going to be positive, so plus F2 times 3. So now we can solve for F2. We can say that F2 equals 10 over 3. And then, roughly equals to 3.33. And then from the first equation, we can say that F1 equals 10 minus F2 is going to be equal to 6.67 newtons. Okay, so now hopefully you should have a bit of a kind of an understanding of what a moment is, sort of this rotational force, as well as how we can use moments in statics equations, very, very simple ones for now, to solve for unknown forces that we might have. Okay, and then finally, I want to just bring up what we call sort of a statically indeterminate problem. So there's many situations and a lot of real-world situations where you're not actually going to be able to simply use statics to determine the forces. And I'll show you sort of a little example of one now. So say we have, again, we'll just draw a bar, but this time we're going to have 4 points on it. We're going to say this is A, B, C, and D. And then we're going to have 4 forces now. We're still just going to have our F still coming down B, and then we're going to have F1, F2, and F3. Okay, so let's see what kind of equations that we can write using these forces that we have. So we might start with the sum of forces in y equals 0 equals F1 minus F plus F2 plus F3. And then, we might take, say, arbitrarily the sum of the moments about point C, and we'll set that to 0. And now we're saying that that's going to be negative 2F1 plus, I should probably put in distances here. Let's just call these all of these are just going to be 1, right? Negative 2F1 plus F, and then plus F3 as well. And then let's also take the sum of moments around B. So do the sum of moments about B equals 0, and that's going to be equal to negative F1 plus F2 plus 2F3. Okay, great. You might be thinking we have 3 equations and 3 unknowns, and we have a whole bunch of other moment equations that we could still come up with, and we could throw these on, and we should be able to solve. But actually, if we label these equations 1, 2, and 3. If we were to take equation 3 and subtract equation 2, what we'd find is that we'd get f1, right, minus f, then there's no f2 there, so we get plus f2, and then again, plus f3 equals 0. And this is equation 1. And so what we find is that these are not actually what are called linearly independent equations. And you can play around with this on your own, but any combination of moment equations that you can come up with, they're always going to sum down to this, and one of them is going to actually be completely irrelevant, right? So one of these doesn't actually give us any new information. We can combine them and we just get a different equation. So really we actually only have 2 equations here, and we have 3 unknowns, and so there is no way to solve for f1, f2, or f3. A lot of the ways that we get around that on the team is sort of making worst case assumptions, right? So if we're saying, well, this load f is going to be distributed f1, f2, f3, if we can't determine what f1, f2, f3 is, we might create, say, the worst case decision. Let's say that f1 equals f2 equals f3 equals f, right? Which is obviously not realistic. But if having each of these forces being big is bad, then by overestimating them, we know that we're going to be on the safe side when we're designing components. Okay, that's the end of the first lecture on statics. This time we kind of assumed what our unknown forces were, or rather, we already kind of had them in place in all of our examples. Next time we'll be talking about joints and how we're going to determine what reaction forces we have at which points.